Okay, example 6. Find the displacement of an object from t equals 2 to t equals 3 if the velocity in meters per second of the object at any time t is given by this function. So we need to recognize this as working backwards. So if I want to know the displacement from a velocity function, I need to take the antiderivative of the velocity function in order to find the displacement function. This is where this gets tricky because you're going to have to read carefully. Is this moving forward? I have displacement and I need velocity, so I'm going to take the derivative, or I have to go the other way. So really what this is asking us to do is integrate from time 2 to time 3 of this function that's given as the velocity function. Of course, we would need to do this in terms of time. So in order to do this question, we're going to have to use substitution. So what are we going to let u equal? I'm going to let u equal the stuff in brackets, t cubed plus 3t. Take the integral du dt, so taking the the derivative of u in terms of t. Oh my goodness. 3t squared plus 3 will be my answer here. Now, looking at what I have as my numerator, I might want to see that that is actually equal to 3 factored out, t squared plus 1. And then I'm going to rearrange this so that I have dt, because that's the one I'm going to want to replace. So dt is equal to du on 3 multiplied by t squared plus 1. And then what are my new boundaries? Okay, so my lower boundary is when t is equal to 2, what does u equal? So u was defined as t cubed plus 3t, so 2 cubed plus 3 times 2. So 8 plus 6 is 14 is my new lower boundary. And then the upper boundary is when t is equal to 3. So what does u equal? U would be equal to 3 cubed plus 3 times 3. So 27 plus 9 is 36. Now I'm going to make my new function. So my boundaries are going from my lower boundary of 14 to my upper boundary of 36. I have t squared plus 1 as the numerator over u squared. And then I have du on 3 times t squared plus 1. And my t squared plus 1 is going to cancel. That's the point of the substitution rule. And then what am I left with? I have a 3 on the bottom, so I'm going to factor that out as a 1/3. And I'm going to be needing to take the integral of u to the power of -2, bring that up to the top in terms of u. So what is the antiderivative of u to the -2? That would be u to the -1 on -1. And so when I tidy that up, I would have -1 on 3u being evaluated from 14 to 36. So I have that this is equal to -1 on 3 times 36. Subtract -1 on 3 times 14. And that is equal to -1 on 08, plus, because two negatives make a plus, 1 on 42. And when you put those two fractions together, you get 11 on 756. Now, the question was, find the displacement of an object. If my velocity is in meters per second, then this answer needs to have the units meters, displacement, distance. There we go, 11 on 756 meters. Okay, a further look at trig. How fun. Determine the indefinite integral of sine squared x dx. Well, if I tried to let u equal to sine x, then du dx is equal to cos. Well, that's a problem. I don't have a cos in here, so that's no good. So the substitution rule is not going to work like that. So I'm going to have to try and do something different with this trig. Okay, so I'm going to go to my formula sheet because I don't have, substitution's not working for me. So I'm going to go to my formula sheet and I'm going to see that cos 2x is equal to cos squared x minus sine squared x. Now I want sine squared x. That's what I'm looking for. So what about if I say cos 2x is equal to 1 minus 2 sine squared x, because cos 2x has 3 different possibilities. So let's maybe use that one instead. Okay, so I'm just looking on my formula sheet and I'm going to use this identity because it's the one in terms of sine squared. I'm going to rearrange this. So I'm going to, let's see, make this be 2 sine squared x on the left would then be equal to 1 minus cos 2x. And then I could divide by 2. So sine squared x is equal to 1/2 minus cos 2x on 2. All right. Then I could use this to replace my sine squared up here. So let's do that. So the integral of sine squared x dx, this is just using identities to make it in a form that I can have a rule to do my antiderivative. So 1/2 minus 1/2 cos 2x in terms of x. And then what is the antiderivative of 1/2? The antiderivative of 1/2 is 1/2 x. And then what is the antiderivative of cos 2x? So leave your constant there. You have to remember back to your rules about these trig functions. So if I'm asked to take the antiderivative of cos kx in terms of x, this is a rule we did back in chapter 9, it's equal to 1 on k. Sorry, not cos, it would be sine now. Sine of the argument kx. So if the argument has a coefficient, you need to divide by that coefficient. So in our case, the k is 2. So this is going to be 1/2 times 1/2, I keep saying cos, silly me, sine of the argument 2x plus c. So when you tidy that up, you get 1/2 x minus 1/4 sine 2x plus c. So basically, anytime we're asked to integrate sine to the power of x, cos to the power of x, where both the m and the n are even, we can basically use that identity formula. You can factor out the half if you want. This is the same as what we just did if I distribute the 1/2 through. You can use these formulas. So you can use an identity when the substitution's not going to work on trig. Okay? In this example, we have an odd degree. So that little rule we just discovered isn't really going to help us. So we're going to have to do something different. So in this question, I'm still going to have to do some identity work to help me get to a spot where I can take the derivative. Okay, so I'm going to expand out my cos to the power of 5. I'm going to say that's the same as cos x multiplied by cos squared x times cos squared x. Now I'm just using my exponent law rules. If I add up all those exponents again, I'm going to get 5, right? If you're multiplying with the same base, the rule is to add the exponents. Now the reason why I did that is because I have an identity for cos squared x, and I'm not going to use the same one I was just working with, the cos 2x. I'm going to use the Pythagorean identity. So sine squared x plus cos squared x is equal to 1. So that means that cos squared x is equal to 1 minus sine squared x. Okay? So bear with me, and you'll see why I'm going to do this in just a second. All right, so 0 to 3 pi on 4 cos x, and then my cos squared x are going to get replaced with their identity. And then I'm actually going to expand those together, or multiply those together. So I'm going to use FOIL to expand these. Okay. And this is actually leading me to be able to use my substitution rule. Okay. When I expand this out, I'm going to get 1 minus 2 sine squared x plus sine to the power of 4. And now I have something in terms of cos and sine. So I'm going to use my substitution rule. I'm going to let u equal to sine, just sine, because the derivative of sine is cos. And when I rearrange that, I get that dx is equal to du on cos x. And so now I'm going to do my substitution. Whoops, I need my boundaries first, sorry. Left boundary would be when x is equal to 0, u is equal to sine 0, which is 0 at 0 radians or 0 degrees. And my right boundary would be when x is equal to 3 pi on 4. U would be sine 3 pi on 4, which is equal to root 2 on 2. Okay, let's substitute in. So this is going to go from 0 to root 2 on 2. And I have cos x multiplied by 1 minus 2u squared plus u to the 4th. And du on cos x replaces the dx. And then the cos x's go away. And I'm left with just a nice little polynomial to integrate. So this would be the derivative of 1 is u minus 2/3 u cubed plus 1/5 u to the 5th, being evaluated from 0 to root 2 on 2. And then I have to put that all in. So I would have root 2 on 2 minus 2/3 times root 2 on 2 cubed plus root 2 on 2 to the power of 5 times 1/5. And then all of that is subtract. When you put 0 in, you get 0 for every single term. So it's just a matter of tidying this up. And when this is all tidied up, we get root 2 on 2 minus root 2 on 6 plus root 2 on 40. Ooh, each of those terms. Okay, I'm almost out of video time. See if you can get that all to reduce nicely to 43 on 120 root 2. Fancy stuff. Okay, so in this case, because I had an odd exponent, I worked a little bit differently with my identities to get to a spot where I could actually use the substitution rule. All right, that's the end of 11.3. Good luck on this chapter. Email me if you have any questions.